Hello friends. Today what we'll do is we'll discuss about formation of steam, and later on we will be discussing about the properties of steam and also solve some numericals on that. Now, as you are aware, we were discussing about this concept of steam in boilers, and boilers are mainly used to generate steam in order to run turbines, that is steam turbines. But how is it that steam is produced, and what kind of properties does it possess? So today in detail we will see about steam formation. Obviously, we know that or what we see around water, it exists in a liquid form. Now the same water can exist in three different phases, that is in a solid phase, liquid phase and a gaseous phase. And in a solid phase we call it as ice, and then we have the liquid phase which we normally see, and then we have the gaseous phase which is called as steam. But what we need to understand is in order to have this change of phase occurrence, some amount of heat needs to be added. So when we conduct this experiment and explain the whole process using a temperature-enthalpy diagram, what we will be doing is we will be assuming a few things. There are a few basic assumptions. Okay, so what we will do is, for example, in this part, that is the first sketch A, which I have named as A, we have taken water, that is 1 kg of water at 0 degree centigrade. Now, ice also can exist at 0 degree centigrade. So if I take 1 kg of ice at 0 degree centigrade and start adding heat to it, the concept or the phenomena what we see is there will be no rise in temperature, but there will be only change in phase. Okay, so that heat which is going to be added is called as the latent heat of condensation, and latent always means hidden. Okay, so it does not exhibit itself in the form of rise in temperature, but it is hidden. So we have taken 1 kg of ice at 0 degrees, we have already added some heat to it, and then water is now available at 0 degrees, and this is, let's say, 1 kg of water. We have a kind of a piston cylinder arrangement. This entire experiment has to be conducted under constant pressure. So the pressure that is exerted has to be the same, at all the stages. So that is the first assumption. Then the second assumption is, since we have a kind of a piston cylinder arrangement, the friction between the piston and the cylinder walls is negligible, or it is almost zero. That is the second assumption. And the third assumption is, apart from the base, what we are seeing, the remaining faces are perfect thermal insulators. That is, no heat is going to escape from the side partitions or the side walls of the cylinder. Only heat can be transferred to the cylinder from bottom. So we have taken 1 kg of water, we have placed the weight, a known weight, and the water is at 0 degrees, and we start adding heat to it. Okay, so this point is represented at A here. Okay, so where we have just started adding heat, there is no enthalpy, and similarly the temperature is 0 degree centigrade. Now, as we go on adding heat to it, we will find that at some point the water starts boiling. So you will also see that because we are adding energy, there is going to be some work which will be done. The piston that has been shown here, it slightly gets raised because it occupies more volume and it starts boiling. So the temperature at which water boils at a given pressure is called as the saturation temperature. In normal terms we call it as the boiling point, but actually it is called as the saturation temperature. So what we have done is, from this point we have added heat, the temperature has risen and it has reached point B. So what we have at point B is, it is still complete water, but the entire water has started boiling now. And this temperature is called as the saturation temperature. Now we further add heat to this. Okay, so when we further start adding heat to the boiling water, what happens is there is steam generation. So water slowly starts getting converted into steam. So in C, that is sketch C, we see that there is some water which is boiling, still boiling, and there is some steam also which is produced. Okay. Okay, so this is a mixture of steam as well as water. So here somewhere between B and D, you choose any point, it is going to represent C. So just for the sake of representation, I have shown it here. So slowly this water starts getting evaporated and steam is being formed. There comes a stage, since we are continuously adding heat to it, what these pink lines show is heat addition. Since we are continuously adding heat to it, there comes a point when the entire water gets converted into steam. There are no entrained or entrapped water molecules. So that is denoted by D. This whole thing we call it as dry saturated steam. Okay, so the dry saturated steam is represented by this point. Now if you look at the value of Ts, that is the saturation temperature, so we have B and D at the same temperature. That means water is boiling at the saturation temperature here, and we have dry saturated steam also at the same temperature. Does that mean that we have not added any heat? No. Actually we have added heat, but there is no further rise in temperature. So what does this mean? That is, this represents that there is an increase in enthalpy, but there is no rise in temperature, and this is called as latent heat of evaporation. Again, as I said, latent means hidden. So even though we have added heat, there is no rise in temperature. Now once the entire water, here we have only water which is boiling, here we have only steam which is completely dry with no water molecules, and anywhere in between it is going to be a mixture. So once we reach point D, and if we further add heat to it, then we observe that the temperature again slowly rises. So here we can see that from D or to this condition, if we add heat, we come to E. So any point on this line where we see that there is a rise in temperature, this quality of steam will be called as superheated steam. Okay, so this is called as superheated steam, and I have just chosen a point as E. This E can be anywhere, it can be anywhere on this point. And if I draw the coordinate on the y-axis, I represent that as T superheated, that is the superheated temperature. Now superheated temperature or the superheated temperature minus the saturation temperature will give us the degree of superheat. That is by what amount we have superheated. So when we were discussing about boilers, distinctly we didn't see any superheaters in case of a Lancashire boiler, but in Babcock and Wilcox boiler we had those superheaters which were U-shaped. Now the reason is, especially in power generation or power plants, steam power plants, thermal power plants, we need superheated steam because they have superheated steam contains more energy, and that energy can be transferred onto the turbine blades, and we can extract more energy from it. Now once this entire thing is drawn, we call this as the temperature enthalpy diagram, where we have enthalpy along the x-axis, and the units of enthalpy are always kilojoules per kg. That is how much heat is added per kilogram. So as I said, this entire experiment is conducted on 1 kg of water. We have started with 1 kg of water. The entire experiment is conducted by applying a constant pressure. These conditions have to remain the same. They cannot change. That is, I cannot change this W anywhere. The pressure which is being applied needs to remain the same. Because I also remember of having told you that maybe in a place like Belgaum, water will boil at a temperature of about 96 or 97 degrees. When we go on higher mountains, maybe on Mount Everest, water will boil at around 92 or 93 degrees. Only at mean sea level, it is going to boil at 100 degrees. So even though we say that water boils at 100 degrees, it is not the same everywhere. It depends on how much pressure is being exerted. So the entire experiment is going to be conducted at a constant pressure. And also remember the other assumptions. Now when we are adding heat, for example, in order to reach from point A to point B, the total heat which is added, this is denoted as HF, H suffix F, and it is called as the sensible heat. Okay. Then from B to D, even though we have added heat and there is no rise in temperature, it is called as HFG, that is H suffix Fg, and that is nothing but the latent heat of evaporation. And Hg, if I add these two, that is if I add the sensible heat and the latent heat of evaporation, I am going to get the total heat of dry saturated steam. So if I choose any point, then here if I draw this intercept, this will be the enthalpy of superheated steam. I write this as H. So these parameters are needed. What is the meaning of sensible heat? What is the meaning of latent heat of evaporation, and so on? Because when we solve the numericals, normally the pressure value is given, and at that given pressure value, we need to find out we need to read out the values of HF, HFG, and so on. Now, at this point, we have complete water which is boiling. There is absolutely no steam which is yet generated. And at this point we have complete dry steam. There are no water particles entering. So this is saturated water and this is dry saturated steam. The quality of the steam anywhere in between, because steam has already started forming from here. So the quality of steam anywhere in between will be called as wet steam. Okay, and the quality of steam is normally defined by what we call as a dryness fraction, which is denoted by small x. Okay, so all these definitions we will be discussing in the next class, but the dryness fraction is defined as x. So what we need to understand is at this point B, x is equal to 0, and at this point D, x is equal to 1. Okay, so here it is completely dry and here it is completely wet. Now, since we are also going to solve numericals later on, of course we will be seeing the various definitions. What do we mean by sensible heat? How exactly do we define it? And then latent heat of evaporation. All these definitions we will be going through, but we will be solving the numericals. Now, in order to solve the numericals, one important, you could say a small, it's available in a very small size book. It's kind of a book only. It's called a steam table. Okay, so you can buy it from any of the bookstores. You go and ask for a steam table book, they'll give you. And in that, you'll have to refer to those pages which are pressure based. Okay, so that is the first column will be the pressure, and then you have the saturation temperature and so on. Just as an example, from one of the books, I show you, for example, it is mentioned here as a steam table, and if I open the page, you will see a steam table will look something like this. This is one page. Okay, so here what we have is the absolute pressure which is in bar, then we have the saturation temperature, that is Ts, what I have shown there, then HF, which is the sensible heat, HFG, the latent heat of evaporation, and the addition of these two will be the specific enthalpy of dry saturated steam. Then you have specific entropy, specific volume, and so on. Maybe in some numericals specific volume will also be asked. So these independent definitions we are going to study them in the next class through a PowerPoint presentation. Okay, so this is all about steam formation. So please remember the assumptions which are made, and what is the relevance of the various points. Try to remember these sketches and relate them with the temperature enthalpy diagram. Then it becomes much easier for you to remember the whole thing. Okay. So thank you very much.